A very common phrase used in Linux and Unix environments is the fact that everything is a file. And that's not entirely true. It's more accurate to say that everything can be accessed as a file descriptor using common system calls like open, read, or write. The Linux API has made these functions available, these system calls available, so you can use one system call to perform these functions across different file types. Now I'm using the word file type loosely because if you're familiar with the Windows environment, files might end in .pdf or .txt or .exe. The files I'm talking about here are a bit different. I'm talking about networking sockets and named pipes and directories and text files and binaries. And if you're curious of a quick overview of some of the different file system and the different file commands and types that exist, both on Windows, Linux, and Mac, but in this case, mostly just Linux, you can always just run the man to stat command inside of a terminal. To in the man page just specifies what section of the manual you want to look at. In this case, we want to look at the system call manual. So if we hit the space bar, we use our mouse wheel, and we just scroll down a little bit further. Towards the end, you'll see this switch statement here, a sample implementation of this function, and then we see several file types listed beneath it, with them being a block device or a character device, and all the difference between those two are a block device will read in a chunk of a file, or it'll operate on a chunk of a file, whatever that block is, whatever it's specified to be. Whereas a character device, it'll read one single character, 1 byte at a time. Directories, you're familiar with that. It's a folder, or you could also say directory is a file that contains other files. You have your first in, first out / your named pipes. We use other pipes all the time with this vertical bar. If I do like a ps-ef and I try to just grep out, I don't know, bash, that is an example of an unnamed pipe. You can create a regular pipe with make FIFO, but that's outside the context of this video. So you also have symbolic links, regular files, a socket, and then something called unknown. So a default if none of these other file types, none of these other objects match what you're trying to do. So why is this cool? Why is Unix, why is Linux a very great environment for programming? Why is it great for performing system calls? What does it do a little bit differently than Windows? And more importantly, why is it not technically correct to say that everything is a file? So for example, if I run an ls, I do have a file here named foo.txt. I can print it out with the cat command. All cat does is take your file and it outputs it somewhere else. In this case, it's outputting it to standard output. A quick recap, if you're not familiar with some of the different file descriptors or how you may view them, if we simply do an ls tech l on proc $$, and then fd with the two $signs denoting our current shell process, right? If I do an echo $$, we see this is my current PID, my process ID. So doing this ls command on our current PID and looking at what file descriptors are open or accessible, we see that there's 0, 1, 2, and 225. 225, no idea what that is. We can safely ignore it. 0, 1, and 2 are going to be your standard input, output, and error, respectively. So anytime you cat a file, you are actually writing it out to file descriptor 1 standard output. Whenever you're trying to receive some type of user inputs, whether in C or Python or any other scripting or programming language, you're going to be working with file descriptor 0. If you're not sure how you can see these things or how you can debug or troubleshoot them or access them, look at the strace command. So I'm going to run strace with tach-o to specify some type of output file, and let's just call this result.txt, and the actual binary or command that we want to run strace on, system trace. We want to run it on foo.txt. We want to peek underneath the hood to see what system calls are being created. So if I smash the enter key, we see no different results. We see please sub has been outputted, right? Just like if I ran cat foo.text, we see it executed the command successfully. But if I do another ls, we see the result. That text file was created, and we can open that up and see what is inside. Let me actually open this up in Vim and not View. View being a command to open something up in readable mode, and Vim is just a text editor. So we see here it's nice and colored, which is always great when you're trying to read walls of text. It's nice to have that beautiful syntax. So at the beginning, we see the command that is being run, exec ve. So execute this vector or this array, this list of commands. We see user bin cat is being ran. Here's the arguments being passed to it. Foo.txt, we have an memory address. Break is being called. So all this here, all we're doing is setting up the actual address space. So you see a bunch of calls to mmap, memory map, to load these actual addresses into memory, so on and so forth. If you run strace on any command, you're going to see a very similar prologue. The first maybe 40 or so lines are all going to be very similar to one another. So if we scroll all the way down, we see on line 42, let me zoom in and make that nice and large. Here we go. On line 38, we see the system call open at, which is being passed our text file, foo.txt. We see the mode. We're opening it in read-only mode. Why is that? This is the cat command, and we're just using it to print out something to standard output. There's no reason right now cat really needs to have access to write to the file. All it needs to do is be able to read the contents of that file. So we're opening the file and we see the return result is 3. If we go back to our other example where we see the different file descriptors, 0, 1, and 2, those are output, input, and error. So the next available file descriptor that the operating system has access to is actually file descriptor 3. If we were to make more files or more file descriptors, they would go in order, 3, 4, 5, and so on, until you fill up your file descriptor table. Then we see the stat command is being ran on that file descriptor number 3, our foo.txt, and we're just checking the permissions. We're seeing some metadata about the file. We're seeing the permissions, 644, with 6 being read and write for the owner of the file, and then everyone else can just read from it. We see the size, the contents, how long the file is. It's only 11 bytes, right? It says please sub, so that's only 11 characters long. On line 41, we see a call to mmap, memory map, and we're just putting this address here. But what we really care about are these next few lines. We see the system call to read on file descriptor number 3, our file. It's reading in the contents, please sub, and then the new line. I'm not sure why it's reading so many bytes. So the read, if we look at it, man to read, it takes in the file descriptor. So in our case, it takes in file descriptor 3, it reads in the contents to a buffer, and then it needs to know how many bytes am I actually reading here. Am I reading 4 bytes, 8 bytes, the whole thing? For whatever reason, I'm not sure why it is reading this many bytes. That seems pretty odd. On line 43, we see the system call write that will output your whatever text, whatever buffer you give it to some type of output stream, some type of file descriptor. And we're giving it file descriptor 1, which, as we've said a million times at this point, is standard output. So write please sub to standard output. It's only 11 bytes long, so write 11 bytes. And then we're reading in a blank character for some reason. And then we see m unmap on line 41. We did the memory mapping and we got this return address right here, OX7F0B, so on and so forth. And we see that memory is being released. It's being returned to the kernel, to the operating system. And then we're just doing some further cleanup. We see all of the file descriptors that were opened are now being closed because we no longer need them. We're telling the operating system file descriptor table, hey, I'm done with this file descriptor. You can have it back and you can reallocate it for the next process or program that needs it. And then we see it exited with 0. In programming, especially languages like C, you have different return codes, return values, error codes. If it's 0, that's essentially saying there is no error. So it's just a common convention, a standard that programmers like to use. So if you see an error code 0 or exited with 0, it means there is no error. Let's quit out of this. So that's the main gist of this video. Not everything is necessarily a file. We can look at /dev or ls-l/dev, and we can see the beginning of these files, and we see a D here specifying that this is a directory, or C specifying that this is a character device. So not everything is necessarily a file in Linux or Unix type operating systems, but everything can be accessed as a file descriptor using these different system calls. And hey, if you still don't believe me, that's okay. You can believe Linus Torvalds, the creator of Linux, or at least the original Linux kernel. I found this email thread from him from the year 2007. And if we scroll down just a smidge, we see these few lines here. Linus writes that the Unix philosophy is often quoted as everything is a file, but that really means everything is a stream of bytes. So that might even be a better way to look at it. And it kind of rolls off the tongue better than everything is a file descriptor, or everything can be accessed as a file descriptor using a system call. At the end of the day, it's all bytes, it's all data, it's all binary, and these system calls are just a way to interpret it. He goes on to write, in Windows, you have 15 different versions of read, with sockets and files and pipes all having strange special cases and special system calls. That's not the Unix way. It should be just a read, and then people can use general libraries and treat all sources as the same. So just using one way, one system, one API, one function to read. And he mentions here in Windows, there's 15 different versions of read. This was a while ago. This was in 2007. When I was doing my own research, I didn't really see that to be the case. So maybe Windows since then has changed their API. Maybe the way they implement these things is different back then in 2007. Because when I was looking, I only saw a few for reading. For example, we have this read file in file.api.h, and it simply states that it reads data from the specified file or input-output device. If we scroll down, we can see the syntax and what this file actually expects, or what this API, this function actually takes as parameters. With the first one being a file handle. Hey, what is that? If we scroll down here, we can actually read what this parameter is expecting. A handle to the device, for example, a file stream, a physical disk, volume, console buffer, tape drive, socket, communications resource, mail slot, or pipe. Wow, that's a lot. And that's not different than what we saw before with the man stat command when we looked at that earlier. It didn't just accept one kind of file, it accepted several different kinds, very similar to Windows. So maybe Windows has changed over the years. So in this same email thread, if you just control F for like file or file descriptor or everything or sockets, we do get kind of mixed results. We do get answers and that are kind of contradicting to one another. So we see here, Linus is saying, what do you think a file is? With file being in quotes. In Unix, a file descriptor is pretty much anything. You could say that sockets aren't remotely file-like, and you would be right. There is a difference between a file, something saved locally on your hard drive that you're accessing, and a remote network socket that might either be listening on your network stack or is containing a remote connection to a server. That is very different. The functionalities, the use cases, it's going to be totally different than a regular text file or a JPEG file. What's your point? If you can't read on it, or if you can read on it, then it is a file, is what Linus is saying. And he goes on, and the real point is that there are a lot of Unix interfaces that basically only work with file descriptors. So what can we take away from this? Probably not much. Hopefully you guys learned something kind of cool. We ran some different commands. We looked at strace. We looked at some of the different man pages. There's really nothing wrong with saying in Linux everything is a file, or Unix everything is a file. I just kind of like to be a little bit nitpicky, and it's one of those things that kind of bugged me just a tiny bit, just a smidge. Anytime I'm talking with a programmer or another like cybersecurity professional and they say that everything's a file, it kind of makes me like cringe a little bit, just because it's not really a file. It is a file descriptor. It is some type of handle or object that you have into the kernel, and you can interface with it with different system calls like read, write, open, close. And I guess you could argue sockets are kind of their own beast. They're their own thing because you not really using open, read, write, and close with the sockets. You'd use the socket function to create a socket file descriptor, and then instead of reading and writing, you would do your sends and your receives and your accepts and your waits. But that's maybe a video for a different time. So what did you guys learn from this? What did you take away? Do you agree that everything in Linux is a file, or do you think it's more accurate to say everything is a file descriptor? I would love to know what you guys think in the comments down below. And as always, take it easy and see you guys in the next video.